Hello students, welcome to Lucky Learning. Here in this video, I am going to discuss the various instruction formats based on three most common CPU organizations. A computer will usually have a variety of instruction code formats. It is not just one instruction format, it can have multiple instruction formats. It is the function of control unit within the CPU to interpret each instruction code and provide the necessary control functions needed to process the instruction. So means we have different instructions, so that control unit is going to interpret what type of instruction it is, what to do with that instruction is going to be determined. The most common fields found in the instruction formats are operation code field, address field, and mode field. We call I bit is called mode bit, opcode, and address. And when I is 0, it is called direct address, and when I is 1, it is called indirect address. And address field is designating either memory address or it is a processor register. And operation code field is going to specify what type of operation it is to be performed. The operations specified by the computer instructions are executed on some data that is stored either in memory or in a processor register. Operands are in memory are specified by the memory address, and operands residing in the processor registers are specified with the register address. A register address in a binary number, a register address is a binary number of k bits with k bits register address specifying 2 power k registers. Thus, a CPU with 16 processor registers that are numbered from R0 to R15 will have a register address of 4 bits. Why? Because there are 16 processor register. It is in 2 powers. We have to represent as 2 power 4. To address each register, we require how many bits? 4 bits. Computer may have instructions of several different lengths containing varying number of addresses. The number of address fields in the instruction format of a computer depends on the internal CPU organization and internal organization of its registers. The most common CPU organizations are single accumulator organization, general register organization, and stack organization. In single accumulator organization, all operations are performed with an implied accumulator. It means all operations by default assumes one of the operand is there in the accumulator. The instruction format in this type of computer uses only one address field that is going to specify address of the operand, and the other operand it is assumed implied accumulator, means by default accumulator. And the second CPU organization is called general register organization. It means computer is going to contain multiple processor registers. It are numbered from R0, R1, R2 dash dash, Rn minus 1 when there are totally n registers. The instruction format of this type of computer needs 3 address fields or 2 address fields. And 3 address fields are needed to specify 2 operands, and one is the result, one for result. In 2 address fields, both will be used as an operand and one of the register will be used as a result. And the third CPU organization is a stack organization. In stack organizations, operands are by default within the stack. And the operation type instruction do not need any address field. Why? Because that operation is to be performed on the top operands of the stack. That's why these instructions are called zero address instructions. And push and pop instructions need an address field to specify which operand is to be pushed, or the popped operand from the stack is to be stored into which operand, that is to be specified. That's why operation type of instruction do not use any address fields. We call it as zero address instructions. These are the three most common CPU organizations: single accumulator organization, general register organization, and stack organization. Now we'll see a single accumulator organization example. In single accumulator organization, add X. Here, X is specifying the memory address. In single accumulator organization, it has default processor register called accumulator. That default processor register is called accumulator. It means that accumulator value already had some operand that is to be added with value in the memory at location X. Both are added and the result is stored by default into the accumulator. When it comes to the general register organization, it requires to have two addresses or three addresses. Let us an example, add R1, R2, R3. It is a meaning that R2 and R3 are added. The result is stored into R1. It means it requires to have three addresses to specify of three registers. Here in this example, add R1, R2. It means R1 and R2 are added. The result is stored into R1 register. Here, how many addresses to be specified for specifying this instruction? Two addresses. Similarly, for this, two addresses. For this, we have two addresses. When it comes to the stack organization, push X, the value in the memory location at address X is stored into the top of the stack. Whenever you say add, this add instruction does not require any memory addresses. Add instruction by default, it is going to pop the top two operands and perform the operation. Because to specify this instruction, we don't specify any address fields. We can say these kind of instructions are called zero address instructions. Here we will understand one simple illustrative example with which we have to write 0, 1, 2, and 3 address instructions. Here I am assuming the instruction is x equaled a plus b into c plus d. It requires addition, multiplication, it requires addition and multiplication. And for one transfer operation from memory and register, general register for move, and two transfer operations to add from memory and accumulator, that is called store and load instructions. Assuming operands A, B, C, D are in the memory and result is also stored into the memory at location X. Now we'll see how to write three address instructions. What is required? First, R1 should have the result of A plus B. So means we write an instruction add R1 comma A comma B. What is it meaning? Memory at address location A is added with memory at address location B and the result is stored into R1. Now in this instruction we are specifying the register 1 address, A location address, B location address. Three addresses we are representing. Similarly, C plus D, it requires to be stored into R2, that is add R2 comma C comma D, so that finally R1 and R2 is to be multiplied and the result is to be stored into X, right? Now these are the computer instructions with respect to three addresses and these are the micro instructions. And when it comes to the two address instructions, two address instructions requires the operand is to be bring into CPU register. First A we brought into R1. So it means memory at address location A is brought into R1. Then it requires to perform addition with B. Add R1 comma B. What does it mean? R1 contains the value of A that is added with value in the memory at location B and result is stored into R1. Means the result of A plus B there in R1. Similarly, move this C value into R2 and add that R2 with D, and the result of C plus D there in R2, then perform multiplication between R1 and R2, and the result is stored into R1. Final result is to be stored into memory at location X. Now R1 value stored into memory at location X. In all these instructions, we were using only two address fields, then we can call it as a two address instructions. When it comes to the one address instructions by default uses implicit accumulator. This is single accumulator organization. What it requires, load this A value into accumulator. Memory at location A is loaded into accumulator. Then it requires to be added with B. A is already in the accumulator. Then when add B says, that is accumulator content is added with memory location at B and the result is stored into accumulator. Now this result is in the accumulator. Now to perform C plus D, again C is to be loaded into accumulator, but accumulator contains the result of A plus B that requires to be used to perform the multiplication. That's why the result of accumulator is to be stored into some temporary location, store T. So accumulator value stored into some temporary location in the memory. Then load C, load the memory value into accumulator and add D. That memory value at location D is added with accumulator. Result is in the accumulator. Now this value in the T, next it has to perform multiplication with T. That accumulator value is multiplied with value in the location at T. The result is stored into accumulator. Now final result is in the accumulator. This final result, it is to be stored into the memory at location X by using the store instruction. In all of them, the instructions is using how many operands? Only one operand. So that we call these are one address instructions, which uses single accumulator organization of a CPU. And zero address instructions. Zero address instructions uses stack organization. Simple. To evaluate this expression, it requires that expression is to be converted into postfix form. Now the postfix notation of A plus B star C plus D is AB plus CD plus star. Now how to have a zero address instruction? Simple. If it is an operand, it is to be pushed, push A, push B. Then if it is an operator, simply perform operation. Now what happens with the case of push A? The A is moved into the top of the stack, B moved into the top of the stack. Whenever you say add, the top two elements of top of the stack is going to be replaced with A plus B. Next, push C, push D, then add. So that top two elements are C and D, that is added and stored into the top of the stack. Then perform a multiplication. That multiplication requires top two elements are to be popped. One is the result of A plus B, another is the result of C plus D. Between them, we have multiplication. The result is stored into the top of the stack. Once the expression is evaluated, the result is on top of the stack. The top of the stack result is to be stored into the memory at location X. It means it is to be popped and stored into X. These are called zero address instructions because operation type of instructions do not require to specify any address field. We call zero address instructions. And here we have one more type of instructions called RISC instructions. What are the RISC instructions? Called reduced instruction set computer. The instruction set of RISC processor is restricted to the use of only load and store instructions when communicating between the memory and CPU. And all the other instructions are executed within the registers of the CPU. Previously, we have seen instructions where instructions are executing on the data stored in the memory also possible directly. But when you have seen this RISC instruction, it requires to bring the operands into the CPU registers, then only it can able to perform the operations. A program for RISC type CPU consists of load and store instructions that have one memory and one register address. And the computational type of instructions like add, sub, mul that have three addresses with all three specifying the processor registers. It is important. All are representing the processing registers. Now look at the example A plus B star C plus D. It requires every operand first come into the CPU register, then only perform the operation. Because in RISC architecture, we can't perform operations like addition, subtraction, multiplication directly on the memory location. First, it has to bring into the CPU registers. Look, load A into R1, B into R2, C into R3, D into R4. Next, what we have to do? R1 and R2 is added and the result is stored into R1. R1 and R2 is added, result is stored into R1. Next, R3 and R4 are added, result is stored into R3. Between these two, it requires to perform a multiplication and the result is stored into R1. And final result is stored into X. So R1 value stored into memory at location X. These are the micro instructions that requires to explain the operation of these computer instructions. These are the RISC instructions of the expression. And hope you have understood the various instruction formats, that is 0, 1, 2, 3 and RISC instructions based on the three most common CPU organizations. Those are single accumulator organization, general register organization and stack organizations. If you like the video, do like and share with your friends and subscribe, and don't forget to click the bell icon for the regular updates. Thank you.